Let me welcome you on today's session, today's lesson, and it is my nice pleasure to welcome on our university, on our faculty, on this floor, maybe professional from the automotive industry and research and technology from Technical University of Graz, Associated Professor, Dr. Lotov, Mario Hirz, and he will here for us, for our audience, to introduce their workplace, their research projects, and their maybe personal stuff, and especially some topics, how to say, basic topics about the motivation why we should care about this part of technology and what they do on their workplace. So Mario, we are here for you to hear carefully, and it is your auditorium.
Thank you very much, Petra, for the invitation to being my host these days. I'm very happy to be here in Brno. My name is Mario Hirz, and I arrived on Sunday. Yesterday we had a lecture with students of Professor Baxand, and I visited some laboratories here, and I was really amazed about this cluster that you have here with university, with research centers. It's really great. And today I was asked to divide my talk in two parts. In the first part, I will introduce myself and the Institute of Automotive Engineering at Graz University of Technology. I have prepared some slides, what we are doing here on research, and some videos to show you examples. And this will take about 20 minutes to 30 minutes. And after that, I will talk about the transition in the automotive industry that we have today towards electrification. And I will put lights or views from different sides on that electrification stuff. I will talk about legislative boundary conditions that push forward this transition. I will talk a little bit about technology, so electric drives, combustion engine drives, the strengths and weaknesses. And then I will put some more effort regarding CO2 emissions under holistic consideration. So for electric car, it's clear it does not have exhaust, but there are CO2 emissions, for example, for the production of the car, for the provision of electricity to drive the electric car. And I will compare that and will show you how a combustion engine-driven car behaves in comparison with electric or a hybrid car. And at the end of my presentation, I will talk a little bit, just a few slides about alternative fuels, hydrogen. We often hear about the use of hydrogen as energy storage, synthetic fuels, so e-fuels, and then I will conclude with a short outlook regarding the market behavior, the sales in the next years in the automotive industry. Okay, let's start with an introduction of myself. So I'm Associate Professor at the Institute of Automotive Engineering at Graz University of Technology. I have a PhD in combustion engines, so I'm a mechanical engineer, and I come from the combustion engine side. And after my PhD, I was asked to build up a new department for, we called it automotive mechatronics. So it's electronics, electrics in cars. And here a large share of my research is related to electric mobility, electric drives, and I will come to that more detailed this evening. Besides my job at the home university, Graz University of Technology, I'm a professor at Tongji University in Shanghai. We have a close cooperation with Tongji in Shanghai. We also have a student exchange program. And I worked for some time in United States, in Tampa at the university. And this winter I'm in Thailand, in Bangkok. We do a winter school there, so it's much warmer than here. In January, we have 30 degrees in Thailand, so it's not a bad idea to make a winter school there. And so I'm international, well-networked here, because automotive industry, automotive research is also worldwide networked. A few words to my university. So I go further here. I don't need to say something about Graz. Graz is in the south of Austria. We have about 300,000 people, a little bit less, so it's smaller than Brno. With agglomeration, we have about 500,000, so 500,000. And what's interesting in Graz, we have 4 universities and about 55 to 60,000 students, so it's a very young, dynamic city. And one of these 4 universities is my university, the Graz University of Technology. And here we have 13,000 students, so it's smaller than the Technical University here in Brno. And in my university, we have 7 faculties for architecture, not agriculture, architecture, civil engineering, electrical engineering and communication technology, mathematics, physics, chemistry and biotechnologies, computer science and mechanical engineering. And my Institute of Automotive Engineering is in the faculty of mechanical engineering. Let's have a look at my institute. So we have 3 departments. The one department is those of the head of the institute, my boss, Peter Fischer. His department is related to the, let's say, traditional classic mechanical engineering aspects in automotive development, structure dynamics, finite element calculation, noise, vibration, harshness, durability, and this stuff. The second department of my colleague, Professor Eichberger, he's related to vehicle dynamics, and he has 2 research groups, the one of my colleague Cornelia Lex about tire research, and Arno Eichberger is focused on driver assistance systems and automated driving. In my group, I do it also. We work in the area of automated driving, but the difference is here we consider humans in the car as driver, and I work on robots. So the cars that we develop in my group don't have a steering wheel or pedals anymore. And Arno Eichberger is doing very much research in the interaction of humans and machines. Finally, my group, it's the largest group in the institute this time. We have 3 research focus, and I will introduce that to you in the next slide. So transport, innovation and environment, electric mobility, and virtual product development. I have, for each of this group, I have 1 slide prepared so that I can show you what we are working on. Lectures and teaching, I think I don't have to talk a lot about this here in the university. We have basic lectures in automotive engineering. We have specialization lectures. For example, I have a lecture of automotive mechatronics, innovative powertrains. Then where is it? Commercial vehicle technology, measurement techniques, and so on. So these are the specialization lectures in the area of automotive technology. And laboratories, collaborative lectures, as it is usual in the university. Here I would like to start now with examples, and I want to show you what we are working on. I just have a question. Do you see something here behind the cameraman? Is this okay for you? Because I stand here to show you the screen, and if you don't see, just move. We have space enough here. Okay. Or you sleep very well behind the cameraman. This is another opportunity. Okay, the first group, transport, innovation, and environment, it's related to technologies of the future. So here we think about technologies in 5 years, 10 years, or beyond. And students love this group because it's very innovative and creative. And what are we doing here? We think about new vehicle concepts. For example, here a car with a foldable wheelbase for making it shorter for parking. Or another example is robotic charging. So here we had a project with BMW and automotive supplier where we want to develop a robot that plugs in automatically for electric charging. The idea behind is to use that in combination with automated parking. So we have established here, or we had a project where in a parking house, in a parking lot, you park your car, and if it is electric and if it should be charged, it registers to the charging robot, and when the charging robot is free, then it drives autonomously to the charging robot, gets charged in 20 minutes, 30 minutes, and then it drives back. So in that way, the charging robot can serve much more than only one car. It drives in, drives out, and in the meantime, you can do your work or going shopping or whatever. So it's done autonomously. And this works. We have shown it last year in Munich at the automotive fair, IAA, in a use case. And I have prepared some videos just to show you what we are doing here. Give me a second, I change the screen. Where is it here? Yeah, so this was the first stage. Here you just see our robot and the car parking in. This car was not autonomously parking. We have a student used for that because we did not get from BMW an autonomously parking car. And then the robotic system identifies the car with video-based object recognition, identifies the position of the charging lid, and then plugs in. And this is a high precisely process because these standard plugs are not built for robotic manipulation. We do it by hand, and with the human by hand, we can manage it somehow. With the robot, we must be very exactly when placing that. So it's about a 1/10 of millimeters. And this was one of the tasks one of my PhD students was working on. And after that, after charging is finished, it plugs out, it closes the lid, and the car can exit the parking space. As I said, in a larger development step, this was shown last year at a fair in Munich. Another project related to this here, I just stopped the video because it shows the same thing twice. Another thing was a robot that drives to the car where the car does not need to go to the robot. So the robot drives to the car and then the same plugging in and charging the car. This is just an early prototype because the challenge is how to bring the electricity to the robot. Here we did it with a cable, and you see it's a small cable, so it was not high power charging. If you have a heavy cable, this of course is much more tricky. And on the next step, but not shown on this video, we realized that the robot takes a plug that is in a wall box, for example, at a parking place, and then plugs in, and then drives to the next car and takes the plug. The challenge here is that you need space. When the cars park very tight, the robot cannot really go in. So therefore, I'm not so convinced. It's a nice exercise, but I'm not so convinced if this will really succeed. Okay. So let's go back to presentation. Okay. What else are we doing? My next research group, e-mobility and alternative drivetrains. Here we develop operating strategies for hybrid cars, so for energy optimization. We had a project with BMW, for example. Or another large area where we have 2 PhD students working on is the optimization of electric drive axles. So electric drive axles consists of electric motor, inverter, and a gearbox that is typically not shiftable. Most of the car have not shiftable gearboxes here. And this drive axle should be optimized in terms of performance, but also efficiency and space requirements, so they have to fit into the car, and of course costs. Cost is a big issue here. And here we have developed, together with a large international supplier, Magna, perhaps you have heard about Magna Powertrain, a new generation of drive axles, and I also have a video. It's a little bit of advertising video, so I will skip the beginning, but just to show you what we are doing here. Where is it here? I shifted the first advertising part. But a little bit later then, you see these drive axles can be used in front axle and in rear axle. And they have to be very compact. You see here that the space demands are very small, very compact design to have space for luggage, to enable efficient vehicle packaging. And here we developed numeric optimization methods by the use of Pareto optimal solutions. So we have multi-dimensional optimization, typically between 20 and 50 parameters. And this reaches a complexity we cannot really display with our typically used diagrams or measures. So we developed here a higher dimensional optimization algorithm that handles this large number of parameters. Yeah, as I said, it's advertising. There always the sun is shining and the grass is green. Okay. Okay, so this is our electric mobility or electric drive groups. What else are we doing? Let me see. Yeah, the next research group in my department is related to methods, development methods, virtual product development, simulation, and a large share is related to design, computer-aided design. We work here with the programs that are typically used in automotive industry, CATIA or Siemens NX or Creo. And we do not only apply these tools, we program in the CAD tools. So we develop, for example, programs that support ergonomics layout, where ergonomics layout is done automatically. Or packaging, vehicle packaging is a very interesting issue in the beginning, in the concept phase of new cars, space requirements, and other solutions. And one topic that is also done in a very intensive way in my department is virtual reality to support the engineers in the early design phase. So in the conception of the vehicle, where we can show by use of virtual reality how the different elements in the car interact, including the driver and the passenger, because they have to fit into the car too, of course. And here I also have a short video. Let me see where it is. It was, again, a work with Magna, where we developed or we integrated virtual reality tools into the conception of new vehicles, into the layout of new vehicles. This is one of my PhD students here. And the tricky thing was to combine the real human and the virtual environment. So as you see here, this engineer is making section cuts through the vehicle layout, is evaluating design, also ergonomic studies are done here, accessibility, and all that stuff that is related to packaging and ergonomics layout. Yeah, the other group, so then the next one is not my group. This is a colleague of mine in another department, Cornelia Lex. She's working on tire research. This is an interesting topic. You could imagine tires we have since more than 100 years, and they work very well. So rubber tires are perfect. So what is the need for research of developing of new methods? Cornelia is working on tire friction estimation in real time. So the friction between tire and road is a very important parameter for control systems. If it is electronic stability control, anti-lock braking system, and others. And even more important when we think about automated driving functions or driver assistance functions. So the system should know the friction between tire and road to react in a correct way, and that in real time. So for example, when you drive today, it's a little bit slippery, and perhaps it snows over the night, and you drive on a snowy spot or an icy spot on the road, the system has to be informed about that in real time, that in case there is a braking event or you are cornering, the system reacts in the right way. And here, my colleague is doing a lot of simulation and measurement in this field. Automated driving, here the example from my colleague Arno Eichberger. So he measures the interaction of humans and machines. We have here a test bench, a driver assistance test bench, where we do a lot of investigation in predefined boundary conditions. We do it with hundreds of test persons. So male and female, different ages, different experience driver, and we measure the reaction and the capabilities of the human driver to interact. This is of very great importance when it comes to a certain takeover demand. So, for example, when you drive with the automated driving function, as it is available in the newest Mercedes-Benz car, so this level 3 highway pilot. For this, it's just brought into the market, I think, this year, in January this year, where you are allowed to read a newspaper. So you can do this. It's allowed. The car is homologated for that. Under certain conditions. It's just on the highway, in a jam, in a traffic jam or that. But you can read a newspaper. But if there happens something the system cannot deal with, you have to take over by hand. And here you have very short time. So you hear a beep, and then after 2 seconds, 3 seconds, you have to take over. And this transition from the automated driving functions to the human driving function is very critical, because if the human driver makes a mistake, there can happen an accident. And the responsibility from the time of the beep, from this overtake command, is at the human driver. And here we do investigation how to support this overtaking, for example. Or other research is related to how to the behavior of human driver, how they react in different situations with bicycles, with motorcycles, pedestrians, and so on. Yeah, the last group of my boss, Professor Fischer, is related to this typically mechanical engineering topics of finite element simulation, by NVH, durability. Here are some examples from brake system optimization. I think I don't go into detail here too much today. Besides that, we have research vehicles. Hello, good evening. We have research vehicles and do much measurement on the road. So with small cars, this is a small electric car, or there is a BMW with driver assistance functions, and also in the truck industry, heavy commercial vehicle industry, we have continuously research projects. Here we do sensor measurements, investigation of laser-based sensors, LiDAR sensors, camera sensors, radar sensors. I have shown some examples yesterday in the lecture. We, of course, have hardware test benches here, a brake test bench for measuring the brake vibrations, the noise, but also the capability of the brake, the performance. Tire test bench here, then some powertrain test benches for electric drives here, for example. We have battery simulator. This equipment, what we need for powertrain development. Also some sensor test benches. This is an example of a high accurate test bench for position sensors of electric motors. You are electrical engineers here, so you know we need a very exact position detection of electric motors to control isochronous or synchronous motors. For both, we need these sensors with a very high accuracy and efficiency. And what we do here is we improve these sensors. We measure them, we work with sensor companies and improve these sensors. Yeah, and finally, of course, we have student teams. I had the opportunity yesterday to visit the Formula SAE team. Good evening, hello. And to have a talk with them, and in my university we also have student teams. We have this Formula SAE team. I will try to press the button. Yeah, Formula SAE, this is racing. Very interesting here, they shifted all to electrics, to electric drives. So also yesterday we had this discussion. This year was the first year where they built an electric-driven racing car, and it's faster than those with the combustion engine. We experienced that over the past years, and most of the teams shifted to electric. It is faster because with the electric drives, we have more opportunity for torque vectoring. This is very cool. So the best teams have all-wheel drive, front-wheel and rear-wheel drive with one motor for each wheel. And when you corner, you can adjust the torque very accurate. And when, as a visitor, when I look at it, it's amazing. They drive a right angle nearly. So really very fast. They have a very high driving dynamics. And this, of course, for racing is really very cool. Here we have the opposite of racing, or it's another kind of racing. So to save energy, we had a world record car, it's some years ago, 2014, with this Shell Marathon. And we have another student group that is more related to, let's say, mass production cars, of cars that could be on the road with homologation. Here this IBEX, which is very close to a real car or to a mass production car. So students are very enthusiastic in doing these competitions. Okay, yeah, so with this, I'm at the end of my introduction and the introduction of my institute and what we do in research. Perhaps a short break before we go into the large presentation. Are there some questions or remarks from your side?
Yeah, maybe I have one. In the last slide, there was a consumption of the car 1 kilowatt hours per 1,000 kilometers. Is this a reality or? Yeah. But it was supported by pedaling. So it was not only the
partially human.
Yeah, it's partially human, but only one driver. Yeah. It's an amazing number. I didn't believe it when I saw it. I think the racing was in Australia, because there are different disciplines. There are solar mobiles,
and World Solar Challenge. Some team. Do you have any?
In the World Solar Challenge, we did not participate yet, but we have some cooperation with Australian universities. And in September, I was in Melbourne, and they did show me their World Solar Challenge car. It looks similar with this, but with additional 4 square meters solar cells on it. Yeah. Okay, some other questions, remarks?
We'll take some short
breaks. 2 minutes, 3 minutes break, and then we will start. Okay.
My top of the colloquium series of the presentation, and today lesson has a name, transition of propulsion technologies on the way of carbon neutral. Mobility as a challenge or opportunity, how we can improve the technology for the future, and motivation for the construction, for the engineering, for the research, and maybe for you as a student to accelerate your studies. Yeah, so
okay.
It's your auditorium.
Thank you very much, Peter. Yeah. Before I start, I have to say I'm an automotive engineer. That means many things that I will present today are very much biased by automotive research, and we have close cooperation with car manufacturer and supplier. And I would like to give you some insights in this transition of propulsion technology that is going on here. When we talk about transition, we have more or less 3 main drivers. So what is pushing the car industry today? It's legislative boundary conditions to reduce emissions. This is the topic I will go very deep inside today, and I want to discuss today. But besides of that, we also have the topics of digitalization and automation. So digitalization means that we have more and more digital systems in the car. We have internet in the car today. We have driver assistance systems, and also the control systems in the car, and comfort systems, and whatever is more and more going into electronics, into digital systems. This means a challenge for the car industry, because they have to change their supplier, they have to change their development processes. And when it comes to automation, especially automated driving, this is a big challenge here. But of course, it provides great opportunities. So I will not go into detail here today, but there could be one or two in other lectures only to talk about automated driving. The third one is also very interesting. It's the new mobility concept and business models, where we see that in the future, less share of cars will be owned by private persons. This is due to the growing cities. So in cities, we have congested areas and not so much space for parking. And it is due to the costs of a car, so the loss of money, the purchase cost, investment costs, and so on. And here we see a clear trend that it goes into car sharing, to use mobility as a service, so to not own a car, but just to use it when it's needed, when demanded. And this, of course, corrupts the traditional business models of the car manufacturer, because the car manufacturer, initially, what do they want? They want to sell cars. But when this changes, with this mobility as a service and these new business models, at the end, they will sell a lower number of cars, which is a big challenge for car manufacturers today. I just did read a publication of the German community of car manufacturers, VDA, Verein Deutscher Automobilhersteller. It was 2 days ago, where they announced that the number of sold cars per year will not have a level anymore as it was in 2018. In 2018, we had nearly 100 million cars sold worldwide. So it was some kind of peak. And due to Corona crisis and other crises, whatever, we are here to this time at about 60 million or 65 million, so a considerable decrease. Of course, it will increase again, but the publication mentioned we will not reach this 100 million anymore, and the car manufacturer have to react on that. And that's the reason why car manufacturer also invest into new mobility concepts and take part to learn how to handle this new, perhaps area of transportation, of people mobility. So it's also a very exciting topic, but I will not go into detail that, because then we would stay here all over the night with my presentation. So I have about 2 hours, and therefore I will focus on the propulsion systems, which is one very important aspect in the transition of automotive industry today. What are the driver of this change of propulsion systems to electric? It's mainly the legislative boundary conditions. And when we look at the legislation, we have two types that influence this transition. The first one is the reduction of harmful exhaust emission. The second one is the reduction of the CO2 emissions. I keep it separated here because it addresses different challenges, different aspects. The reduction of harmful exhaust emissions is related to the harm of the exhaust gases to the health of the people and to the environment, but not directly the climate change. We have here in total about, just to give you an idea, when we look at the exhaust emission of a modern car, we have less than 1% of the exhaust are harmful emissions. So it's a very small amount, but it's poisonous, and therefore it's restricted for sure. This reduction of harmful exhaust emission is very strict, regulated. I have here an example. I know you cannot see it from the last rows, but it's just to give you an estimation. Here is the timeline, and here is the emission limit, and we see it's reduced. So when we look over the past decades, it's reduced a lot. The different colors just indicate different markets. The blue one is United States. It's the most tough NOx legislation of this emission nitrooxygens. The red one is the Chinese, and the brown one is the European. And we see that they are decreasing. And in Europe, we have now the next level. It's the Euro 7 exhaust emission, which will come into force in 2025. And it means a further restriction of the harmful exhaust emissions. I will come to that point later because we come now to a situation where combustion engines become more expensive because of the very complex exhaust gas after treatment that is necessary to reach these limits. This is especially the case for diesel engines. In the diesel engines, we need very complex and very expensive exhaust gas after treatment. And this is one reason, and I come to that later, more detailed, this is one reason why we see a strong decrease of diesel engines. Car manufacturers go out of diesel in many areas because they are too expensive at the end. They are not competitive anymore, even if a diesel engine is very efficient and can reach low fuel consumption, but in the end, because of this very sharp definition of the limits of harmful exhaust emissions, they become so expensive that it's not really a good business, or the customer would not pay so much for the diesel engines anymore. So this influences the politics of the car manufacturer. The second, and this is perhaps the even more tough challenge for the car manufacturer, is the reduction of greenhouse gas emission, especially CO2 emissions. Here we have in Europe a clear target, the target of the carbon neutral continent in 2050. It's a so-called Green Deal released by the European Commission in the end of 2019. And with this vision to be a net zero neutral continent in 2050, this affects a lot of businesses, not only automotive industry, but on automotive industry or transportation industry, it has a very strong impact. Now we can say, okay, 2050, it's, perhaps I will live not in that time, so I don't care. But I have to care because there are intermediate steps defined. And one of these intermediate steps is to reduce the CO2 emission 50% in 2030. 2030 is not far away. I hope I will be alive in 2030. And so I have to care. And when we look at this behavior of CO2 emissions, it's related, it's related to 1990. So the baseline is 1990. And the target is in 2030 to be here below 50%. And this slide shows different branches and the behavior of the CO2 emissions. So we have here agriculture, we have buildings, electric power generation, very relevant in your faculty, the industry, the waste management. And we see that all of them can manage it to reduce their CO2. Only the transport, no. The transport had a still increase in CO2. And this is the reason why there are so tough targets for the transport sector. So the transport sector has to change significantly to reach the target. Well, the European Commission not only announces the targets, it also announces technologies that should be used to reach that target. And for the transportation sector, there is written down electrification of cars and trucks. It's a clear strategy written down. Then we have hydrogen as a fuel. The application is not so clearly defined. It might be for trucks, for ships, aviation, we can discuss, but hydrogen as a storage element for fuel is announced here. I come to that later more detailed. And the third one is the use of synthetic fuels. Synthetic fuels are carbon neutral fuels. I will show you in a few minutes how it works, where we also can operate a system with theoretically zero carbon or low carbon footprint. This is related to transportation. Besides that, the European Commission supports green electricity production. Whatever green is, we can discuss this, or it is discussed. So with the latest announcement, nuclear power and natural gas is seen as green. I will not go into detail here too much, but it is seen in politics. And another aspect that is relevant is carbon capture and storage. So for the industry mainly, we have processes in the industry that demand very much heat for the steel production, for example. And the idea is to, for these high demanding and high CO2 producing processes, we take the CO2, we capture it, and we store it in deep drawn holes or whatever in the earth crust, however we can store that. So to reduce the output of CO2. Yeah, looking at the transport sector, how large is the impact of the transportation sector? And we see here the global anthropogenic emissions that are more or less parallel to the CO2 emission, where we have the worldwide transportation share is about 23%. For Europe, it's 28%. So it has a certain share. The others are agricultural, industry, and so on. Looking at the transport emissions, we have about 5% railway, about 11% aviation, about 11% the ships, so naval industry, and about 74% road caused emissions. And when we look at the road transport, we have a little bit more than the half by cars and small vehicles, and a little bit less than the half by heavy-duty vehicles. So in total, when we multiply the 75 or 74 with the 23, we have about 17% of the CO2 impact stems or comes from transportation. So it is a relevant factor. In Europe, it's a little bit higher because we have a higher share of transportation. How does the legislation react on that? The legislation prescribes fleet emissions. And these fleet emissions limit the CO2 emission of the sold cars in a market. And the interesting thing is that these fleet emissions target to the car manufacturer. So the car manufacturer will be punished if they do not reach that targets. Counted is the fleet of cars that is sold and registered in 1 year in the market, for example, in 1 year in Europe. And the average CO2 emission must be below the values that are shown here. And for Europe, for example, we have this time 95 grams per kilometer. So this is the average emission limit. And if a car manufacturer is above that value, they have to pay. And they have to pay a lot. I'll show you on the next slide. What also shown here is that for different markets, so gray is United States, red is China, Japan, Europe, we all have the same trend. And even in the area of Trump in the United States, it did not change. So it was the same. Whereas in the United States, we have to distinguish between the states. In California, they are more tough. In Texas, no. You can imagine why. Anyway, what does it mean? 95 grams per kilometer. I've calculated the fuel consumption. It means 4.1 liter gasoline per 100 kilometer or 3.6 liter diesel fuel. This 95 grams per kilometer can be achieved with a modern car that is lightweight, that is perhaps hybrid driven. We can reach that in the test cycle. It's possible, but the next target, and we look at that target for 2030, it's 59 grams. And 59 grams is about 2.5 liter per 100 kilometer. And this is physically not possible for combustion engine driven cars. We cannot do it. We cannot improve. Okay, we can do it for a very specific small car that looks a little bit like the world record car. I've shown it before for my students, but this is not a normal car. And in that way, we see that the legislation already started to kick out the combustion engines from the market. We have now, overall, in 2035, the ban of combustion engines. I come to that a little bit later. But even before, in 2030, the car manufacturer need a considerable share of electric cars sold a year to reach the 95 grams target. And this is the reason why all the car manufacturers introduce electric cars. They do not do it because they are so funny or whatever, because they want to save the world. No, they do it perhaps they want to save the world. I will not assume that they don't want. But mainly they do it because of legislation. Because the legislation sets a target where they have no chance to reach without electric cars. And we have a lot of cooperation with car manufacturer, and I know that they play with the numbers. They make prognosis, how many cars, how many percentage of shares of cars do we need to sell in 2030 with combustion engine, with hybrids, different types of hybrids, with electric cars to reach the target. So it's a very hard calculation, a very accurate calculation done by the car manufacturer. Okay, yeah, what are the consequences? This 95 grams per kilometer is punished if it is not reached by the car manufacturer, and it is punished with 95 euro per gram violation per car sold. Just to play a little bit with numbers to give you an idea how expensive this is for the car manufacturer, let's take Volkswagen. Volkswagen Group sells about 3 million cars a year in Europe, so all these Volkswagen brands. So we have about 3 million cars. I just write down here, for the example for Volkswagen, we have 3 million cars multiplied with 95 euro. And when we assume that they cannot reach the 95 grams, let's go 5 grams above, let's say they reach 100 grams in their fleet, I multiplicate it with 100. It's a number of, let me see, 100, 6, 10, 1. Do you have a calculator? It's so late in the evening. I think it's about 3 billion euros, something like that. 3 million multiplied with 95 multiplied with 100. 10 hoch 10?
Yeah, 10.
10. So is it 10?
Yes.
No, I did a mistake. Because the number is too high. Even this would be too high. I will not punish Volkswagen so much. My mistake was I wrote down 100. But I have to write down 5 grams because I'm 5 grams higher than the allowed 95. So 5 grams. And then it's it's about 1.5 million, right? Billion.
1.5, yeah, 1.4 billion, correct.
1.4 billion euro. Yeah, now I'm fine. We can punish Volkswagen with 1.4 billion. They have the money. Anyway, but what I want to show you here is that it's expensive for the car manufacturer. So if they go above the limit, they have to pay really a lot. And we saw that in the last years because these 95 grams are in force since 2021. So we are in the second year now. And last year, for example, Fiat did not reach the target. So there are some car manufacturers which really get in trouble. And this is much money for the car manufacturer, no doubt. Okay, there are some details. I will not go here in large. There are some phasing in regulations in the first years where the car manufacturer gets special credits for electric cars or when they produce the car with green electricity, so CO2 neutral production. Pooling is allowed. So in the Volkswagen Group, Porsche is included. Pooling is also allowed by contract. And there was the funny story with Fiat, Chrysler, and Tesla, where it's not published, but the rumor goes that Fiat Chrysler pays about $300 million a year to Tesla, that Tesla agrees to go into the pool so that they don't have to pay so much fee in the European. So it's a good business for Tesla. And there are reliefs for small manufacturers. So Ferrari is extra and some other small manufacturer, but this release will also fade out with 2030. So in that time, then also Ferrari has to be in line with this legislation. What are the reactions? What are the strategies of the car manufacturer in the short term? So short term is the next 5 years. It's about optimization. So we will see here optimized combustion engine with lower fuel consumption. We will see smaller combustion engine. This CO2 emission legislation is the reason why the large combustion engine die out. So nearly no 8-cylinder engine for new cars or 6-cylinder engine. There are some, but only with very small number of production. Then they have not this big effect on the fleet consumption. So we have 3-cylinder engine, smaller engine with a higher efficiency, and electrification. So hybrids, plug-in hybrids, electric cars. I will talk about that more detailed. For the long term, it's very clear it's electrification. So all the car manufacturers go into that direction. They have no choice, more or less. There are some research going on regarding hydrogen vehicles and synthetic fuels, but from the status of legislation today, it's not accepted. Hydrogen vehicles, yes, it could be, but synthetic fuels is not accepted as CO2 neutral, even if it is. So this is the status today, but there will follow some discussion in the next years. Well, let's look into the propulsion technologies. And here in the next section, I would like to compare combustion engines, electric drives, and hybrids. And before I do that, some physics. Don't be afraid, stay in the room. It does not hurt, it's just for explanation. I want to point out the very important aspect that we have with electric drives in terms of recuperation. When we look at the driving resistances, in very rough, we have the rolling resistance, we have the air resistance, we have the climbing resistance, and the acceleration resistance. And when we have this in the driving situation, and here is just an example where we drive with a car uphill and accelerate the car, we see the rolling resistance is relatively small over the speed. The air drag, when we have the driving power, the air drag increases with the factor 3, so power of 3 with the cubic function. Then we have the inclination and we have the acceleration. For example, when we drive uphill and overtake a truck, something like this here. And when we look at this power that we have to put into the car for this driving situation, we have the possibility to recover acceleration and inclination energy by braking. And we can do this with two types. So for inclination, we can do it with all cars, because when we go uphill and later we go downhill, we have some benefit from that. For acceleration, we only can do it during braking. And when we have a conventional car with combustion engine, what happens with this energy that we have put in? Do you have some idea? When we brake the car, what happens with the energy?
It's converted to heat.
Yes, absolutely right. It's converted to heat. So we heat up the environment, which is perhaps also not so good for global warming, but the impact is small. But anyway, the energy is gone. We cannot recover it. In case of an electric car, what can we do? Yes, recuperation. That means we can operate the electric motor as generator and store a certain share of energy in the battery. We have done some measurements with your car, with Tesla Model S, for example, and depending on the driving situations, we reached up to 85% energy recovery in the battery. So it's really good what we can do here. And even if we have some kind of hybrid with a smaller battery, in normal driving in the city, we have 30, 50, 60% energy recovered instead of released to the environment. And this is a point that we can only use with electrification. We cannot use that with a combustion engine. So a big point for electrification. The air drag and the rolling resistance are lost. We cannot recover them, but even if they are relatively small here, it points to the importance to improve aerodynamics and to improve the rolling resistance of the car, because it, for example, it influences the energy consumption during driving, and at the end the driving range when we have electric car, for example. Okay, here I have on a nutshell the strengths and weaknesses of the 3 propulsion systems. I will go through very quickly, just in the overview. Conventional drives with combustion engines are cheap, are established, and we have long driving distances. It works very well. At the weakness side, we have a thermodynamically limited efficiency. What does it mean? The combustion process is based on the so-called Carnot process that defines the theoretical efficiency that could be achieved by a combustion engine. And this Carnot process is very simple, so it's very simplified. It's defined by the upper temperature and lower temperature in the combustion chamber. And these temperatures are limited. The lower temperature is more or less the ambient temperature where we aspirate the air. And the upper temperature is limited to materials, because when we get too hot, the piston melts. The upper temperature is combustion temperature, not wall temperature. In the combustion, it's about 2,200 to 2,400 Kelvin, something like that, perhaps a little bit higher, but it's limited. And due to this limitation, the theoretical optimal combustion engine cannot reach a better efficiency between 70–75%. That's it. It's physics. And now we have to go to the real engine. We have friction, we have losses because of not perfect combustion, we have heat losses, we have blow-by, we have whatever losses in the combustion engine, so that in a real combustion engine, we reach in a car, when we look at automotive engines, best efficiency of about 42–43% in a diesel engine, but only in one point. I'll show you on the next slide. And in a gasoline engine, we reach about 35 plus minus a little percent in the best point. This is the efficiency that we can reach in an automotive application, so it's limited. There are improvements. I'm often asked, how much can we make it better? Can we make it better? So the potential for further improvements, it's limited. If we would take all the technologies that are under research into one engine, we have done a simulation about that, so what's the potential of combustion engine? We could not reach the 60-gram target with a car. 2.5 liter would not be possible with a normal car. Even if we put laser ignition, variable compression, whatever into the combustion engine, we could not reach it. Electric drives are much more efficient. So when we look at automotive electric drives, we have efficiency in the range of 60–75%, considering the entire drive chain, so with battery, inverter, electric motor, real driving conditions. And when we look at the real driving conditions with the combustion engines, we are in the area of 25–30%. So we are more than double better with the electric drive. We have no local emissions, and it's really comfortable driving. So if you have the chance to test the electric car, test it. Perhaps don't take the cheapest on the market, take a good one and test it, and you will see it's really comfortable and good driving. On the other side, we have the very expensive battery. So in a modern electric car, and I will show you a slide about that, the costs of the battery is up to the half of the car. So depends on the size of the car and the size of the battery, but we talk about 30–50% of the cost of the production cost of an electric car is only the battery. It's expensive. We have shorter driving distances and longer charging times. Here, it's a supercharger. It takes about 30 minutes to charge to 80%. This, of course, takes more time than 3 minutes gas charging, of course. And as a very important point, and I come to that later, the environmental friendliness depends on the technology of electric power generation. So when we produce electric power out of water, it's fine. When we do it with coal plants, it's not so good. I have some slides about that. Hybrid drives is the third one. Hybrid drive is the transition technology. So I assume that in the next years, the car manufacturer will introduce only new cars with combustion engine in combination with hybrids. Because with hybrids, we can improve the efficiency and reduce the fuel consumption. In that way, hybrids will be very significant in the automotive industry for the next, let's say, 5 to 6 years, but then the share will decrease because we have the zero combustion engine target in 2035. So, but for the next years, hybrids for sure are very relevant. Drawbacks of hybrids are that it's complex. We have to integrate electric drive and combustion engines, and the potential to reduce fuel consumption is very much related to the technology of the hybrid. So some cars are mild hybrids, where the largest effect is to write down it's a hybrid, just for sales. It's not really a big effect on fuel consumption reduction. Other cars are full hybrids, Toyota Prius, for example, or others, which can reach 20–25% fuel consumption reduction. And others are plug-in hybrids, where we have the possibility to charge the battery on the grid. I come to that later. Yeah, here I have it on this slide. So hybrid technologies are available in very different configurations. I do not have the time today to go into detail, but depending on how the combustion engine and the electric motors are arranged, we distinguish between serial hybrid, parallel hybrid, and combined or power split hybrids. And all of them have different strengths and weaknesses in their applications. As I said, with CO2 reduction potential, perhaps 5% with a mild hybrid, up to 50% with a plug-in hybrid, but it depends on how the customer uses the car. A friend of mine is working at BMW Fleet Management, so he's responsible for these business cars of BMW. And he told me, last time we were at a beer in a bar, and he told me, yeah, because I asked him about the plug-in hybrids. And he told me, yeah, they have very good plug-in hybrids at BMW, 5 Series, for example. They are very good business cars. But when they come back from the fleet after 3 years or something like that, they are replaced. With more than 80%, the charging cable is originally packed in the rear trunk. That means this plug-in hybrid was never charged. Whatever. So here it really depends a lot how the car is used. If we plug in it, we can drive electric. If we don't plug in, we just have a full hybrid, more or less. And battery electric drives. I think I don't have to talk a lot about the configuration of electric drives here in this room, because you know more than me about electric drives. But in general, we have electric storage. So the battery systems, it's typically 400 volt. Some cars have 800 volt storage. Then we have the inverter, the power electronics, which has the job to control the electric motor and to convert the 2-phase direct current into a 3-phase, at least 3-phase alternating current. So therefore, the inverter is a very important component. It's a high performance component that performs the control of the electric motor. As electric motor, typically we have a permanent or we have synchronous motors. They can be permanent magnet synchronous or externally excited synchronous motors, or we have asynchronous motors. All three of them have advantages and disadvantages, but I don't have to discuss this here in this room. I think you know that very well. Then we have a simple gearbox. It's a mechanically transmission. Most of the electric cars don't have shiftable gears here, just some sports cars, Porsche Taycan, and some race cars, but most of them have a very simple gearbox and then the drive to the wheels. Here a short overview of the main differences when we compare electric motor and combustion engine. With the combustion engine, we have a certain operating range. So typically, we have an idle speed between 800 to 1000 RPM, and we have a maximum speed, depending if it is a diesel engine, gasoline engine, sports engine, whatever, about 5000 to 6000 RPM. And in this range, the combustion engine delivers power, but because of the limited range, we need a gearbox. So we need a shiftable gearbox, 5-speed, 6-speed, 7-speed, or so on, because of this very limited operating range. In addition, we need a clutch for start driving, because when the car stands still, the engine is running with idle speed, and we need a clutch here for overbridge this speed difference. A clutch is working with friction, and that means losses at the end. With the electric motor, it's totally different. Electric motor, it's very simplified here, so please correct me. But very simplified, we have a high torque at 0 speed. That means for start driving, we don't need the clutch. We just start driving. Then we have a high torque until the field weakening point, and then we have the field weakening area where the torque is reduced, so we reduce the current. But this can be similar to constant power. It depends on the electric motor type, until a maximum speed. And the maximum speed in the, let's say, lower cost region is about 12,000, 14,000 RPM for high performant or sophisticated electric motor. It goes to 20,000, 24,000 RPM. And because it starts with 0, we don't need a gearbox and we don't need a clutch. So we have this large speed range. We have the good behavior of the electric motor for a drivetrain. If I would be in 150 years ago, and I would see these diagrams and would have to decide which motor I would take for driving a car, I would take the electric motor, of course. Because we don't need a gearbox, it has a high torque for start driving, it's the better system. It's a history with the energy storage and so on, why it developed different. But now it changes back. Regarding efficiency, we see here the diagrams of a combustion engine, where in this example we have the best efficiency here in the small area, 35%. And with a part load, the efficiency goes down to 20%, whatever. So in that area where we operate the car the most time, we do not have the best efficiency. But don't tell this to the police when you drive too fast next time. Don't argument that you just want to operate the car in a good efficiency area. I think it will not work. But anyway, for our daily usage, we don't reach or we don't operate the combustion engine in a good efficiency area. With the electric motor, it's totally different. So we have here 80–90% efficiency over a very wide range of the electric motor. I think you know that. Only at part load, at very part load, we have some issues. Okay, we have differences depending on the electric motor type, but in general, the efficiency is another world. It's another dimension here. I always press the wrong direction. So here, what's about complexity? When we compare a car with combustion engine and a car with electric motor, we very easily see that the car with combustion engine has much more mechanical components. So perhaps you cannot read, but it's written down. It's the combustion engine with all the mechanical components, the crankcase, the crankshaft, the valve train, flywheel, whatever. Then we need a gearbox, a shiftable gearbox with all the components. We need the fuel system with the tank, the fuel pump, filter, and so on. And we need the exhaust system, which can be also very expensive, especially when we talk about diesel engines. So we have a long list of mechanical components. With the electric car, the powertrain is much more simple under mechanical boundary conditions. We have the battery, we have the electric motor and inverter, we have a high voltage system, charging system, that's it. So much less components, but not cheaper, because especially the battery is very expensive. I have a cost comparison on the next slide. What does it mean when the car industry now changes from combustion engine to electric? It means that a lot of supplier companies lose their jobs. And this is a serious issue that is much discussed this time, how we can support the European supplier industry to go with this change, with this transition to electric. We have very good companies and very much knowledge in Europe to produce combustion engines and gearboxes and all the components. But when we go to electric drive, this knowledge is fine, but it does not help to earn money. And so we must support the companies to go this step from combustion engine to electric drive. On the other hand, it's also affected to universities. So you are sitting here, the students here, I can tell you, you have great job opportunities. Electrical engineers, control engineers are really searched by the car industry, and they pay much money for beginners this time because they don't have enough stuff, and they really hire a lot this time because they have to build up the knowledge in this area of electric drivetrains. So for the students, you did a good choice. This is a very future-proof study, and you will have very exciting jobs very soon. Just finish your study first. But this is another story. Yeah, the costs. I talked about costs. This diagram was made by a colleague of mine, Professor Liegenkamp in Munich, and his PhD student. And I think from the last row you cannot read, but I will provide you the PDF file. So for those who are interested in the presentation, please contact Professor Baxant. He can share the PDF file to you. Then you have the numbers. Anyway, what you see here is a cost breakdown of a compact SUV. So it's the class of Volkswagen Tiguan, something like that. The direct cost means the production costs. And we see here 2020 and a prognosis of 2030. And when we look at that, the production cost of an average vehicle in this class is about 14,000 euro. Don't ask me why this car costs 40,000 for you, but it's because of the taxes, the development costs, the profit, whatever comes here in addition to the production costs, of course. In comparison, an electric car in the same class is about 20,000 euros. So it's about 50% more expensive, mainly due to the battery. And I have broken down here the different modules in the car. So the black is the battery in comparison to the combustion engine. Here, 8,000 euro for the battery, 3,000 for the combustion engine. Complete combustion engine, including exhaust system. Then we have the gearbox here, and here on this side we have the electric drive, 2,000 euro, so electric motor, inverter, gearbox. And the other components are more or less similar. It's the bodywork of the car, the interior, exterior, and so on. And what's the prognosis for 2030 is that the costs of the battery will go to half, to about 4,000. This is mainly due to scaling effects of battery production. The car with combustion engine, the price will increase moderately, mainly because of exhaust emission after treatment, so the complex system that we need. At the end, it remains a difference of about 10%. So we can assume that in 2030, electric car will still be more expensive than a standard car, but the difference will be not so much. Yeah, let's talk about the impact of propulsion technologies, and here I will highlight the CO2 impact, so the climate warming effect. And when we analyze cars, we have to consider what happens in the car plus what happens in front before the car or before we go into the car with the energy for energy provision. And here we distinguish between the so-called well-to-tank emission. This includes everything for the production of energy. In the car, we have the so-called tank-to-wheel emission. This comes out of the exhaust. So I will explain this diagram. For the car with combustion engine, we have here the production of fuel. So we have the crude oil production, we have the oil refining, the transport to the gas station. In the gas station, we fill in the petrol or diesel into the car, and then we drive the car. The tank-to-wheel emission are here at the exhaust, and they are directly proportional to the fuel consumption. The well-to-tank emission are in the range of about 10 to 20% of the tank-to-wheel emission. So when a car, for example, has about 100 grams per kilometer CO2 during driving, about 10 to 20% need to be added to represent the production of fuel. It's in this wide range because it differs between diesel and gasoline, and it also differs between the processes applied. For the electric car, we don't have CO2 emissions in the car. An electric car has no exhaust, but we have the provision of electricity. So here, it plays a big role how electricity is produced, and here I have prepared a slide. Let me see, here it is. Different technologies of electricity production. I think you know that behavior. I have here the different technologies of electricity production and the CO2 impact in grams CO2 per kilowatt hour electricity produced. I've written down here CO2 equivalents. This is a typical term that we use in life cycle analysis where we convert different values into a CO2 impact. So for example, when we have methane generated, we convert the impact of methane into CO2 value. So we convert into one parameter because it's more easy to represent. And when we look at that, we see that fossil-based power generation has a high CO2 impact. Of course, because we burn hydrocarbons. And when we burn hydrocarbons, we produce CO2. So the brown coal with more than 1,000, hard coal about 1,000 grams per kilowatt hour. Oil, natural gas is not so bad, about half of the coal power plant. And then we have here a row of so-called renewable technologies, solar cells, wood chips, biogas, wind, hydropower, and they are in the range of 20 to 50 grams per kilometer. It's a complete other system to produce electricity. What's included here is also the production of the power plant, the service of the power plant. That's the reason why a hydropower still has 20. Solar power has 50 because the production of the solar cells needs a higher effort. Nuclear fuel is rather good in terms of CO2, but not considered here is the high costs of nuclear power plant and the deposition of nuclear waste or the risk of nuclear accidents. It's not included here. I just focus on the CO2, and here we see that nuclear power has a pretty good impact. And when we look at this electricity production in different countries, we see here very, very different behavior. This diagram shows the mix of CO2 impact, the so-called electricity mix, in CO2 in grams per kilowatt hour in average over a year. So it's not to a time, it's in average over a year. And it shows the impact in terms of amount of electric power generation in terawatt hours per year. And here we see the large markets or the large countries. China has about 7 terawatt electricity production a year. United States, a little bit more than 4,000. And the Europeans, 27, about 3,000 terawatt hours a year. And what we also see is China has in average about 600 grams per kilowatt hour, United States about 400, EU about 300. And I have added some more countries in detail. Norway, this is the blueprint of green electricity production. They have mainly water, so hydropower, very low. France has a large share of nuclear power, I think 75% or something like that. Canada, also a large share of nuclear power. Brazil, water power, and some other countries. Germany is with about 400. I just have here the largest countries. By the way, if you want to know the electricity mix of your country, I have here a link. And we can look at Czech Republic. Let me see. This electricity map is just a map that shows in real time the CO2 footprint. And when I look at this, I have about 500 grams per kilowatt hour in Czech Republic today. This is because of the weather. We have no sun, no wind, and yeah, therefore, let me see if it works. 460 is the average per year, I think, yeah. I just wanted to see it online in real time, but yeah, this is the reason. In Austria, we also have about 220 because we have much water power in Austria. And of course, this influences now the CO2 impact of electric car. It's how electricity is produced. I will not calculate that. On the next step, when we go more accurate into this analysis, we have to consider not only the driving of the car, but also the production of the car and the service of the car. So whatever appears in the life cycle. And this I would like to show you on the next slide. So the so-called life cycle consideration, where we compare different technologies. Oh, wrong direction. So here it is. And this life cycle assessment includes the entire life cycle of the product. In case of a car, we have it materials production, so the extraction of raw materials, processing of materials, transportation. We have the vehicle manufacturing, the components, the logistics, or the parts in the car. We have the usage, where we learned about the well-to-tank and tank-to-wheel emissions. We have the driving mileage, the driving behavior, so how are the car used. And we have the end of life with the recycling, with the disassembling. And when we consider all these processes, we can calculate a total CO2 footprint of a car. And I have done this and want to show you some results. Let me see. Yeah. In a rough overview, we have done this for a number of cars. And here, this slide, I want to show you the general behavior of the different powertrain systems. So I have set here the CO2 equivalent impact, and I have set the car with combustion engines to 100%. I have divided it into the vehicle and the powertrain for the production of the car, so when we produce the car. In relation to the car with combustion engine, the electric car has between 50 to 100% higher CO2 impact. This is mainly caused by the battery. The battery production, the battery materials is very much effort, and due to the fact we have about the same CO2 footprint of the car, including electric drive axles, is provided by the battery. Of course, it ranges, so it depends on how large is the battery, which car equipment with car type we have, so it ranges. But the range is between 50 and 100% higher CO2 impact in production. The hybrid car is in between. So if you have a mild hybrid, it's nearly the same as a standard car. When we have a plug-in hybrid, it can be up to 50% higher because modern plug-in hybrids have battery size of about 10 to 15 kilowatt hours. So it's a considerable battery. And this, of course, increases the CO2 impact of production. This is only the production. I will show you both on one of the next slide, production and use phase. I just want to show you here, we have done this calculation very accurately. So in this example, for a Volkswagen ID.3, so this electric car of Volkswagen, where we have here calculated the contributions of the different main modules in the car on the production-related CO2 footprint. This is the version with 58 kilowatt hours battery, so with the large battery. Here we have 7 tons in production. CO2 is in the production of the battery. In total, we have 14 tons. It's not written down here, but it's 14 tons. It's half. 7 tons is only the battery. Then we have the bodywork of the car. It's a steel body, the electric powertrain, interior, and so on. And we go one more step in detail and analyze the different materials where we have the battery cells as very relevant. We have steel, we have electrics, electronics, aluminum, and other components. One point to the battery cells. An automotive high voltage battery, as used in electric car, is typically a lithium-ion battery. And it consists of a number of cells. There are different types of cells available, and these cells are then combined to modules and to the battery pack. There is a cooling system for the battery, electronics control, a housing, and so on. And in terms of value creation, about 40 to 60% of the costs of the battery is only the cells. The rest is all that other what I mentioned before. And the problem that we have today is that the cell manufacturers are mainly in Asia. So more specifically in China. That means from the status of today, in most of our electric cars, the cells are imported from China. And it's the most expensive part. And this was a little bit overlooked by the European Commission. They did not react early enough on that to recognize, okay, when we shift to electrification, we sell a lot of electric cars, but we import the cells from China, which are the most expensive parts of the car. It's not good for our business and economy. That's the reason why this time the European Commission supports very much the establishment of cell production in Europe. And the first companies that do that are Chinese companies. So, for example, Samsung builds a gigafactory in north of Budapest. CATL, which is another Chinese company. Samsung is not Chinese, it's South Korean, sorry. CATL, which is the largest supplier, builds a large manufacturer, I think one in Germany and the second one in Poland, I think. I'm not so sure about Czech Republic. Is it not yet, perhaps?
The Cattle, the CATL,
yeah, Cattle.
Will build a factory also in Hungary.
In Hungary, yeah, a second one in Hungary, yeah. So they come here because they get much money from European Commission to do that. But at the end, it's the only way to deal with that problem that we would import, or we do import now the cells from China. So battery cells, battery production is a big business and a big politics this time. Anyway, here I go back to CO2 emissions, and we see this is the carbon footprint of this Volkswagen ID.3 and for the production. And this slide shows the energy demand in driving or for the usage of the car. And here I just want to point out it's not only driving. For this car, we have assumed 16 kilowatt hours per 100 kilometer in a moderate driving style, in a normal driving cycle. But we have to add auxiliaries, for example, the heating or cooling system of the car, additional devices that we have in the car, the lights and so on. It's about 10%. And the charging losses. And regarding the charging losses, it varies a lot as a function of the charging power. When we charge the car at home on the plug, we have a very low charging power, perhaps 3 kilowatts, 3.5 kilowatts, and the charging losses are very low because the battery is not stressed. So for low power charging, we have about 3% losses, perhaps 5, not more. But when we charge on a supercharger with 100 kilowatts or even more, Volkswagen does not allow, this car does not allow more than 100 kilowatts. But when we go to 200 kilowatts or higher, the charging losses can go up to 25%. So we have measured this at a Tesla Model 3 with maximum charging power 250 kilowatts, and we had a charging losses of 25%. That means that a quarter of the energy that you pack into the car is released as heat to the environment because we need to cool the battery. So regarding efficiency, the charging power is an important parameter. I just wanted to mention that. Low power charging takes longer, but if you have time, take the choice of low power charging. Normally it's cheaper and the losses are not so high. Here in average, as a mix between high power and low power charging, we have assumed 2.4 kilowatt hours, so that in total we have 20 kilowatt hour per 100 kilometer energy consumption for this car. As next, we have compared the CO2 footprint over the lifetime of the car. And I start with the combustion engine driven car. I just want to mention which cars we have compared, just for explanation. So the electric car was the ID.3. The car with combustion engine was a BMW series, 1 series with 3-cylinder gasoline engine, about 100 kilowatt power. And the hybrid car, I will also show, was the Toyota Prius. So we have 3 modern cars compared. And here we have calculated the effort for production, the CO2 footprint of production, and the CO2 footprint of use. And in a simplified diagram, we see here, this is the car with combustion engine, so internal combustion engine vehicle, ICV. The production effort was 7 tons CO2. So to produce this BMW 1 Series, we have calculated 7 tons for the production. And then over the driving distance, and here we have assumed 200,000 kilometers, it's simplified because it's a straight line. It's not, in reality, not accurately straight because we have service, we have spare parts, and so on, but they do not really influence that a lot. So at the end, after 200,000 kilometers, we have 40 tons CO2 produced. During the ride, we burn the fuel, we produce CO2. The Toyota Prius, as a hybrid car, has about 25% lower fuel consumption. That means it has a lower CO2 output during driving, but the effort for production is a little bit higher, about 20% higher. So the Prius has about 9 tons CO2 in production. But as you see, because of the lower fuel consumption, we have a break-even here below 50,000 kilometers in terms of CO2. What about electric cars? And here, it depends on how the car is charged, or with which electricity the car is charged. At the beginning is the production. So we have 14 tons calculated for the Volkswagen ID.3. I showed you before, half of that is the battery. And we start here, and I have just taken here some countries from the grid from before. Where is it? Here. So I just have taken some countries, and as you see, Poland has a relatively high CO2 impact because of coal power with about a little bit less than 700 grams per kilowatt hour. Norway is very low, and I have just put in here the assumption that we charge the car one time in Norway, then we have nearly no increase during driving. So we have here 16 tons in total, which is significantly lower than with combustion engine or hybrid. But when we charge the electric car in Poland, we end up with a higher value than the car with combustion engine. And this is very important to understand. When we look at this European Green Deal, the responsibility regarding CO2 shifts away from the car manufacturer to the energy provider when we talk about electricity and electric cars. The car manufacturer will do their job. They will convert to electric cars because they have to do. But if the mobility sector is really able to reduce the CO2 impact, is now at the table of the energy provider and of the electricity mix. So when you have, for example, at home a solar station and you charge the car with solar energy, you are on the good side, no question. But not everybody will have the possibility to build a solar station at home. Okay, and in between this range, we have different countries. It's just to give you some examples. So the European mix, we are here with 26 tons in average in Europe. Germany is a little bit higher, Austria is a little bit lower. I think Czech Republic is similar to Germany, so it might be about 30 tons or a little bit more when you charge an electric car here in the public grid and operate it. Out of this consideration, we now can calculate some break-even points, and it's just out of the diagram. So when does it pay back to under consideration of CO2 emissions? So the break-even to the combustion engine and the electric car in Norway is at about 45,000 kilometers, so it's no question here. When we go to break-even in Germany, for example, to the combustion engine, it's about 80,000 kilometers. It's reasonable. But when we look for the break-even in Germany with the hybrid car, it's 120,000 kilometers. This is too much, of course. So it's within the lifetime of the car, but it does not really take the potential of that technology. Okay, yeah, so far to this comparison of the propulsion technologies on the aspect of CO2 emissions. Are there some questions or remarks from your side regarding this topic? Yeah, please, you and then you. Mm-hmm.
The combustion engine with the synthetic fuel have the same pollution like the standard?
Yeah, synthetic fuel is a very good question. I will explain synthetic fuel on the next slide. But to answer your question, the harmful exhaust emissions are about the same as with standard fuel. The CO2 footprint is different because with synthetic fuel, the idea is to take CO2 out of the atmosphere to produce the fuel. Then we have taken the CO2 out of the atmosphere, we have reduced the CO2, then we produce the fuel, we fill it in the tank, and then we burn it in the combustion engine, and at the exhaust, the CO2 comes out. So in total, we have a balance. This is the idea behind of the synthetic fuel. But the harmful exhaust emissions are about the same. It's not much different. Thank you. There was another question?
The line shouldn't be straight because every year the CO2 from the production of fuels and electricity changes.
Yeah, absolutely right. You are absolutely correct. This is not shown here, that every year the electricity mix gets better, right? And over the lifetime of a car, when we assume 200,000 kilometers, it might be 10 years or more, for sure, the electricity mix becomes better. Yeah, thank you very much for that input. This is just taken under consideration electricity mix today. I absolutely agree. Yeah, thank you. Thank you. Yeah, please.
Maybe just a remark. The consumption of internal combustion engine also change in the life of the engine. More older car consume more fuel. Yeah. And we did same calculation for Czech mix and Czech or the car we tested. Mm-hmm. And the changing point in Czech Republic is about 50,000 kilometers. 50,000. But in cars or battery electric vehicles, which is efficient, yeah, not from production of W.
Mm-hmm. I see. Yeah. Okay. Yeah. Okay. It was just an example. Yeah. Okay. Okay. Yeah. Thank you very much. I absolutely agree. We have here aging effects. We also have aging effects on the battery, but in our calculation, we did not change the battery because with a modern electric car, 200,000 kilometers should not be an issue. You don't need to replace the battery. This was different in the first years of electric cars, so 10 years ago or 8 years ago, the lifetime of the battery was not sufficient, but today we can assume that the battery is in the car for the lifetime of the car because we have degradation, but it's not so relevant. Yeah. Thank you very much. Yeah, great. Yeah, please.
I have questions. The calculation of the CO2 production for the battery is computed from the raw materials. It starts from the raw materials. Yeah. Yeah. Would the situation change if we will use
recycling? Yeah. Recycling of the battery is a very important issue because of these valuable materials that we have, and it works. So in general, there are different types of recycling by pyrolysis, so we burn the components and we extract the materials, or by chemical liquids where we take out the materials. So it works in the processes, but it does not pay back. The problem that we have today is that batteries, especially automotive batteries, are not designed for recycling. It's very much effort to disassemble the battery, then to extract the cells, and then when we have the cells, then we can scramble them or recycle them. But it's a very expensive and manual work-demanding task. This will change. In China, they have introduced a legislation that for new cars, the battery must be designed for recycling. So the Chinese market is the first, and we will see coming cars where the car manufacturer have to take care that the battery it's possible to disassemble the battery. One example, a very worse example, is Tesla. Tesla Model 3, they are top in terms of performance and driving range and efficiency. And Tesla is very good in terms of lightweight design. So the Tesla cars are reference for electric cars in terms of the weight. But the battery is not designed for disassembling or recycling. In the latest model, Model 3, Model Y, they even glue the cells in the battery. So they glue it in some kind of thermal foam. This is very good for cooling. This is very good for stiffness of the battery and behavior of the car. But you cannot take out the cells. So this is the challenge here. And you can scramble all that stuff, but then the recycling efficiency will not be very good. So recycling is a very important topic that is not considered enough by the car industry because the materials at the end are available and are not so highly priced that recycling would pay back. There is another approach. It's the so-called second life use of the cells. In fact, when we have these automotive batteries in use after 200,000 kilometers, the battery has still a capacity. We measured different cars with this mileage, and we measured between 70 and 85, 86% capacity of the battery. That means the capacity still works. And after 200,000 kilometers, perhaps the car breaks down, but the battery has some value, and the cells or the battery could be used for stationary applications where it does not make or is not so important to have the full capacity. There are different approaches for that, but at the end, there are some big challenges. The one is the warranty, because when we take used cells, we have to check each of them singly, in a single selection, if they work well. Because when we build this in a stationary battery, in a house, in a basement, and they start to burn, it's not a good scenario. So the quality management of the battery is an issue. Then the question, who takes over responsibility if there is a problem? Is it the car manufacturer? No. Is it the battery second use company? Yes, but they have to be sure that nothing happens. And the third aspect is missing standardization. We have, when we will get back old batteries or old cars, we have different types of cells, pouch cells, pneumatic cells, cylindrical cells with different materials inside. So there is no standardization, and the different cell types and materials have different behavior. It's not easy to combine them. There are some projects with car manufacturer where the cells that are taken back are exactly the same type and material, then it's easier. But with this, we have a lower volume that we can use for that. So with both recycling and second life, it's important, it makes sense, but it's not on an industrial scale today. Yeah. I hope I could answer your question. Yeah. Thank you for that. Okay, some more questions? Yeah, please.
I thank you for showing the electricity map.
Mm-hmm.
We with colleagues believe that this project, like electricity map, could shine a bright light over the energy mix. Thank you.
Thank you. You find it in the internet. Yeah. You know it from the internet. Yeah. Okay. Yeah. I have to say the values. It's just one platform, the electricity map. The values are not always accurate and always correct, but it gives a good estimation. So in a thumb rule, it fits not bad. Yeah. Thank you. Okay, let's continue. What else do we have for propulsion? So in this last section, and then I come to my end. What's about alternatives to electric cars? Alternative fuels. I talked about hydrogen. And hydrogen, I have to say, when I went to school 100 years ago, I learned hydrogen is the fuel of the future. And then I went to university as a student, and I learned hydrogen is the fuel of the future. And today, I tell my students, listen, hydrogen is the fuel of the future. You see the joke of the story. Hydrogen is the fuel of the future since decades. Why is it so attractive? It's the possibility to drive a cyclic process. So the idea is we produce hydrogen by electrolytic conversion out of water. We store hydrogen, and then we can use it here in combustion engine or in fuel cells to produce electricity or mechanical energy. And what comes out is water that we can reuse for producing of hydrogen. So far to the theory. What's about the reality? The perhaps largest problem today is that most share of hydrogen today is produced out of natural gas. With natural gas, I just write it down, we have a main fraction of natural gas is methane. Methane, you know, it's CH4. So where is it? CH4. Methane, it's a main fraction of natural gas. And we see here it's very attractive to produce hydrogen. We have one carbon and 4 atoms of hydrogen. And the process to produce hydrogen out of methane is very cheap. It's a so-called steam reforming, where we blow a hot steam into a large canister, and we let the hydrogen or press the hydrogen in, and then it breaks up so that we have the hydrogen, and the carbon combines with the steam, the water, the oxygen in the water to CO2. So with this we produce hydrogen and CO2. It's not green, but it's cheap, and it's done in a large scale. More than 95% of all hydrogen worldwide is produced out of natural gas and produces CO2. In that way, it doesn't really help for climate or against climate warming. Storage of hydrogen is more or less solved in the automotive industry. We use high pressure tanks. This works. These are tanks up to 700 bar, high pressure storage, carbon reinforced tank systems. It works, but it demands energy to compress the hydrogen and to 700 bar. And just to give you an idea, it's about 10% of the energy content in the hydrogen we need for the compression. So the efficiency is influenced by that. The conversion here of hydrogen then is, I would say with the fuel cell is the state of the art. We could burn it in combustion engines, but the fuel cell is the perhaps more attractive way. And this works too. So the fuel cell operates very well. The efficiency is in the range of up to 60–65% with the fuel cells that we use in the cars. So these polymer membrane fuel cells. And there are cars on the market, Toyota Mirai or Hyundai Nexo, and I think Honda has also a model, but they are not sold on a large scale. It's more or less a technology carrier in the market. So hydrogen can work, but we need the infrastructure and we need the production of green hydrogen, then it works. Where is the application? I see it in the commercial vehicles. So we have had a cooperation with a company in China. They develop and produce hydrogen trucks and hydrogen buses, and they operate them. So this time they have in Shanghai 500 hydrogen delivery service vehicles, so like the Mercedes Sprinter or Fiat Ducato, so in this size. And more than 500, and they work, it works. Of course, the hydrogen is made of methane, but in general, it works. They also operate bus fleets in China. And in Europe, too, there are hydrogen projects. For example, my city will buy next year 2 hydrogen buses, and we will learn how they operate in public traffic. So the technology is here, more or less, but it's relatively expensive, and the production of hydrogen is an issue. What about synthetic fuels? Here, everything is about the so-called power-to-liquid, or the e-fuels. On this slide on top, I have just mentioned the state of the art. This is more or less historically the gas-to-liquid, so we can produce fuel out of methane. It's not CO2 neutral. We did produce, in the Second World War, fuel out of coal. And biomass, we can use biomass to liquid for fuel production. Biomass is not a bad idea. Perhaps you know where The largest share of biomass is applied for fuel production in which country? Does somebody know? Brazil, yeah. They produce it out of sugarcane with a very high efficiency and this ethanol for drive the car, and it works. It works perfect. And the CO2 footprint is relatively low. In Brazil, they have the advantage that they have 2 harvesting periods of sugarcane a year, so it's very effective. But on the other hand, there are some social issues with the native population and the rainforest, burning rainforest. I'm not so sure if this is directly related to the sugarcane plants, but they have some other issues with this. But in Europe, I think a large scale of biofuel will not succeed. We had this in Germany, but it's always a question to use food for fuel. And this is politically very critically seen in Europe. What is about e-fuels? With the e-fuels, and they are much in discussion today, the idea is to produce hydrogen and then to combine the hydrogen and the CO2. The CO2 is taken out of the atmosphere or is taken from CO2 intensive processes, steel industry, for example, where we produce a lot of CO2. We extract the CO2 and we synthesize this hydrogen plus CO2. We synthesize to hydrocarbons, HCs, plus oxygen. And this works. So we can do that, but the disadvantage is it requires a lot of power. So the efficiency of this process is not really good. I have a slide about that. Anyway, in theory, it works. And when we think about that, we can produce a carbon-neutral fuel. When we use, for example, a wind power, no CO2 production of electricity, in electricity production, and we use this electricity to drive this process to produce hydrogen out of electrolytic conversion, and then we combine the hydrogen with the CO2 out of the atmosphere, we have a fuel, we have a liquid. The efficiency is not good. It's about 20%, in perhaps a little bit more, 30%. But if it is a wind power, that is an excess of power, excess of electricity that we cannot store in the other way, the efficiency is not so important anymore. So e-fuels can be a part of an energy system where they can be used for storage of energy. Because in this sustainable or sun-based power plants or wind power plants, we have high fluctuations. When we have a storm in the North Sea, they produce so much power that the energy prices drop down even to minus in Europe. And then when there is no wind, they don't produce power. And with the sun it's the same. When we have a weather as today, the solar system, photovoltaic system will not produce a lot of power. When the sun is shining, yes. So we have these high fluctuations. And therefore we are looking for energy storage, and both hydrogen and e-fuels can serve here. I would like to give you a comparison of let's say, a future scenario where we consider the Green Deal. So here I have 3 cars with different propulsion systems, and all of them are CO2 neutral. So it's the vision of the Green Deal. We have for that we need a CO2 neutral electricity production. So we have here the electricity from wind power, from solar power, from hydropower. And in the first example, we use it in an electric car by direct charging. In the second example, we produce hydrogen with green electricity, and then we drive a hydrogen car. And in the third example, we produce the e-fuel, so the CO2 neutral fuel by use of the green electricity, and then we burn it in a combustion engine. And this comparison is related to efficiency, so to the losses of the process. When we look at the electric car, we have here renewable energy, and then they assume, so it's a publication from Transportation and Environment. The numbers might be a little bit biased, but it's about the range in general. they assume 5% energy losses, so 95% efficiency at the charging station for the electric car. Then we have the charging losses. Here only 5% losses, so we do low power charging in this example. Then the battery losses about 5%. And then when we drive the car, we have here assumed very good efficiency. As I say, 5% and 5% losses only in the electric drive, so smooth driving. And this would result to about 77% efficiency. We have calculated that in my department, we come to a range depending on the different aspects that we consider here, fast charging or worse efficiency in electric motor, but we reach a range between 65 and 75%. So in this range is our electric car. The hydrogen-driven car, here we need to produce the hydrogen out of electricity, and we have about 80%, 78% efficiency with a high-quality electrolytic system. With high temperature fuel cells, we can reach nearly 80% efficiency. So we have here 22% losses for the production of hydrogen. And then we have the storage and transport of hydrogen, where we have the compression to 700 bars or more, and we have the transport. So this is calculated here again with about 20% losses, so that in total we have 60% at the hydrogen gas station. So this is this well-to-tank percentage. In the car, we have the fuel cell here assumed with about 54% efficiency, the electric motor and inverter, so that in total we come to about 30% efficiency of the hydrogen electric car, which is about the half of the electric car. At the end, when we look at the e-fuel, we have the production of hydrogen. We need the hydrogen for the e-fuel. And then we have this synthesis process of CO2 and hydrogen, which is very energy demanding, so that the well-to-tank is about 44%. These are the losses that we have for the production of the e-fuel. In the car, it's simple. We have a combustion engine. In that example, we burn it with about 30% efficiency of the combustion engine in average, so 70% losses, and we have about 13, perhaps 15% total efficiency, which is about a quarter of that of the electric car. What does this mean at the end? Operation of a hydrogen car will be double expensive, minimum double expensive than operation of electric car, and operation of a combustion engine car with e-fuels will be about 4 times more expensive than electric car, because the efficiency at the end represents the costs of that. Not considered here is energy storage, as I mentioned. So it might make sense to have hydrogen production, to have e-fuels, to store the energy of this high fluctuation of sustainable energy generation. But, for my opinion, the e-fuels will be produced, but they will not be used in cars. They will be used in airplanes, aviation, where we need this high energy density. Perhaps they will be used in some trucks or commercial vehicles, might be, or ships, but the cars are the last in the row because it's much more simple to drive it electric. The same we have with hydrogen. It will be produced. It's very relevant, this energy storage concept, but we can use hydrogen for a long row of other applications, stationary, but in ships for heating, as a natural gas exchange or something like that. Okay, now I come nearly to the end of my presentation. I just want to give an outlook and summarize a little bit the market situation for the next years. And here you can read a lot. So when you go into newspapers or journals or even scientific publications, everybody looks into the crystal ball and calculates which cars will be sold, which technology will win. And I have just summarized here a number of prognoses, and 2 things can be said. The one is that combustion engine-based powertrains will be very relevant for the next about 5 years. But after 5 years, so it's 2028 about, the sales of combustion engines, production of combustion engines will decrease because the car manufacturer have to reach this 35 target with the ban of combustion engines. And when we consider the development time of new cars, it's about 5 years. So it's to be expected that from 2028 on, nearly no car manufacturer will really introduce new cars with combustion engines anymore because they fade out over the time. From 2028 on, electric cars will be will have the main share on sales, new cars on the market, especially in Europe. For Europe and China, I would see it in that way. For United States, it might be a little bit delayed. Also different in different states, but it might be a little bit delayed. Another aspect I want to mention here is that we have to distinguish between the numbers of new cars sold and registered and the existing fleet. So I'm not so sure about Czech Republic, but in Austria we have about 5 million cars on the roads, old cars, new cars, whatever. I guess Czech Republic is similar, about 6 million, yeah. 6.5 million cars registered. Registered cars on the road, yeah. For Austria, I know the numbers. We have a market of about 300,000 new cars registered a year. And I guess for Czech Republic, it will be 350, something like that. That means that the fleet is going to be replaced by about, let's say for Czech Republic, 350,000 new cars a year, but the total fleet is 6.5 million. That means even if we would have 100% electric cars sold, it would take 10 years, would be 3.5 million, so nearly 20 years to replace all the cars. This is an important effect to be considered, because when we read the newspaper, we always read about the new cars. But the old cars will be still in the market, and even if there will be acceleration, whereas I'm not sure about that, it might take 15 years, whatever, to replace. So with this, it will be very hard to reach the target of 2050 to be CO2 neutral, because there are still old cars, old vehicles on the market, and with the same we have with trucks and commercial vehicles and so on. And some expect that there will be some kind of Cuba effect. Do you know the Cuba effect? Where the old cars are kept forever, because the people cannot afford new cars or don't want to buy new cars. So this could be an effect that also can be relevant for Europe. Of course, we will have political measures with gas prices and so on. But just, I want to point out, we have to distinguish between the behavior of sales of new cars and the behavior of the fleet, which is much delayed in relation. Okay, yeah, with this I come to the end. Just some outlook or some arguments, what's the way it's going in the next years. This was a study that was made by one of my students. And I asked my student to scan publications in the automotive industry and to analyze research that is done in the automotive industry. And my students did this for the time frame until 2018. So 2015 to 2018. And in this time, the development was done in combustion engine improvement. Fuel injection system, reduction of friction, improvement of emissions, new combustion processes, whatever, alternative fuels, also hybrid powertrains, and a little bit electrification. When you analyze the publications and the research projects in the automotive industry in 2022, it's everything has stopped what had to do with combustion engines. Not in Czech Republic, okay? You are the last bastion here? Okay. Oh, that's good to hear. But at the end, I see it in my university. We have an institute that is the largest university institute in Austria. It's the former Institute for Internal Combustion Engines. There are about 150 people working in this one institute only, and they changed the name last year to the Institute of Sustainable Drive Systems. Yes. Because they have no new projects in relation with combustion engines. And also when we talk with the car industry, where does the money go? They don't develop new combustion engines, except of Czech Republic, because they have to invest into electrification. And perhaps you did read about that. Car manufacturer announced, Audi, for example, announced that they will develop their last generation of combustion engine. I think it will come into market in 2025 or 2026. And then they will not further develop combustion engines. So the car manufacturer published this, with the exception of some markets, United States, China. Because in China, there will be no ban of combustion engines. In China, it's very different. They have very strict regulations in the cities, but beside the cities, they will further allow the combustion engines. China do not ban combustion engines. Okay, yeah, I just wanted to show you, it's the age of combustion engines. I'm very sorry about that because I have a PhD in combustion engines. So 100 years ago, I made a PhD in combustion engines. And I have to say, I like the sports cars and it's nice, but yeah, it's a little bit, very soon it will have a historical touch, you will see. Okay, here's some prognosis. I will not go into detail. I talked about that. What's about, so looking into the crystal ball, electric cars will have a market share of 50% or more on the Chinese market and on the European market. All calculations point to that. United States a little bit delayed, perhaps 30%, 35%. Plug-in hybrids, with the plug-in hybrids, it's a story. They were very popular at the car manufacturer because it was a possibility to sell their cars and to have low emissions in the test cycle. Because for the plug-in hybrids, there's a specific test cycle defined, which considers the purely electric drive. That was the reason why plug-in hybrids have a fuel consumption in the test cycle of 1.9 liter, whatever. And then you test it on the road and you have 6 or 7 liters. But it's not wrong. It's just a consideration that you can plug in and drive purely electrics. But at the end, it turned out that the customer don't care and don't plug in. And therefore, the legislation will consider that in two ways. The one is that plug-in hybrids need larger batteries, so more electric driving range. And on the other hand, it's also discussed to modify the test cycle to be more reality near with the fuel consumption. And perhaps the largest competitors of the plug-in hybrids is the new electric cars with the larger battery, with the better driving range. So it's not necessary to have a combustion engine on board because the driving range is 400 kilometers or even more. And the prices are not so much different. Therefore, I see not a large growth in the plug-in hybrids business. Hybrid electric vehicles, yeah, hybrid we will see. Because with the hybrids, the car manufacturer can very simple and easy and with low invest reduce the fuel consumption of the combustion engine. So more or less all combustion engines will be somehow combined with electric drive. Is it a mild hybrid or full hybrid? Because at the end, it's necessary to reach the emission targets. And for my opinion, the largest competitors to the diesel engines is the hybrid. It's cheaper. It's very simple to combine a standard gasoline engine with an electric motor. You have the same fuel consumption as a diesel, but it's cheaper. It's more simple. You don't need this exhaust gas after treatment with the 3-stage conversion and so on. And the combustion engine vehicles, so cars with only combustion engines will decrease in the market. So I would say from 2027, 2028 on, we will have nearly no combustion engines without combination to hybrids. It's different for other markets, but for Europe, we will have here, nearly all cars will be equipped with electric drive in terms of hybrids or purely electric cars. Okay, with this, I thank you for your attention. I'm here for discussion, of course. It was a pleasure for me to be with you here, and I hope I could show you some things and awake the interest and enthusiasm to the change, to the propulsion technology, to the change in automotive industry. Thank you very much. Peter, is there time for discussion?
It's the time. It's about 30 minutes for discussion. If you want to depart around.
Yeah, that would be great.
So.
Are there some questions, discussions?
Can I? As my knowledge, as far as go, my knowledge or understanding about the directive about the 95 grams per kilometer, there is like a small condition that this 95 grams per kilometer is weighted by weight.
Yeah.
So thus manufacturers do big battery SUVs, so they can make this condition.
Yeah, absolutely right. Yeah, I did not mention that due to time reasons, these 95 grams per kilometer are related to the average mass of a car, which is, I think, 1,350 or 370 kilos, like this. If the car is more heavy, it can have a higher CO2 output, and this line is calculated according to the driving resistances. So when a car is more heavy, you have more driving resistances, and due to that function, it can be moderately higher. Just to give you some numbers, Volkswagen, I think they have to reach 96 or 97 grams because of the average weight of their car fleet. Daimler, Mercedes, and BMW, I think they are in the area of 105 because they have more luxury car, more heavy car, so they don't need to reach 95. They are at about 105. Fiat, only Fiat, not Fiat Chrysler, they have more small cars. They are below 90 grams, I think 89 or something like that. So the weight is in a function that more or less represents the change of the driving resistances. Yeah, that's correct. Yeah. Thank you.
And heavy SUVs, the battery SUVs are considered like zero emission, but the weight of the fleet, average weight of the fleet
of the car. Yeah, that's right. Absolutely. The average weight of the fleet goes up, which supports the luxury car manufacturer. Yes, I agree. Yeah, thank you. Mm-hmm.
I have a question regarding the hybrid cars. We know that there are parallel hybrids and serial hybrids. Mm-hmm. Most of them are parallel hybrids, but I think Nissan or somebody have in production serial hybrids.
Yeah.
Or if you know, how is just now the situation generally about the serial hybrids? Mm-hmm. Are they already in the production? Do they want to produce or focus it, or is the, I would say...
Yeah, a very good question. The serial hybrids have the problem of a worse efficiency. This is the case because in a serial hybrid, the combustion engine drives a generator. Then the generator, the electricity in the generator must be converted in an inverter, stored in the battery. And then when you drive the car, we take the energy out of the battery. We have the battery losses. We have another inverter. And then we have the electric motor. So we have a long chain of energy change. And in total, this leads to a worse efficiency, to disadvantage in efficiency. It's a little bit more complicated because we can operate the combustion engine in good efficiency area. This is possible because independent on the wheel speed. But in total, it has turned out that serial hybrids are not so good in efficiency as combined power split hybrid or parallel hybrid. The serial hybrids that we had in the past in Europe was a range extender vehicle. So for example, BMW i3, perhaps you know this electric car, you could buy this car with a range extender. In the rear trunk, you had a small two-cylinder engine, and when the battery ran out of energy, then you start the small engine and you could continue a ride. And Nissan has a car now, I think, on the Japanese market and Chinese market.
Japan, you're correct.
Yeah.
Some small one. They
yeah.
wanted to come to Europe, but I'm not sure
I'm not sure if they come, but they have a serial hybrid, so as a city car. For my opinion, it's not really an option for larger scale application, but it's a good opportunity for the car manufacturer because it's simple. From the control, it's relatively simple. You just simplify it. You switch on the combustion engine when the battery is empty or the energy demand is high. You have no mechanical drive to the wheels, and the rest is an electric drive axle and the battery. And depending on the battery size, it's a range extender or a direct serial hybrid. So it's relatively simple setup. I also know that some Chinese manufacturers work on that because they get funded as nearly electric cars because the drive is electric, but the powertrain at the end is with combustion engine. So I think from efficiency point of view, it is not the best solution, but from economic point of view or as a range extender, it can make sense in the cars. The parallel hybrids are really loved by the car manufacturer because they don't need to modify a lot. So with the parallel hybrid, we have the combustion engine drivetrain with the gearbox, and the electric motor is placed somewhere in this drivetrain to operate parallel to the combustion engine. In the mild hybrid, it's a so-called P1 or P0 configuration. The most simple one is the starter generator system, where you just replace the electric generator with a little bit more powerful electric motor generator with the belt drive, and then you can start the engine and support a little bit, perhaps when accelerating the car, but that's it. Then there are more complex configurations with a clutch between electric motor and combustion engine. Here you can stop the combustion engine and drive purely electrics. This is used in full hybrids and plug-in hybrids. And there are some other configurations like in the gearbox, the electric motor, or after the gearbox. And also very common configuration is the P4 hybrid, where one axle is electric and another axle is driven by combustion engine.
Isn't it in Toyota?
Yeah, Toyota has it, or Mitsubishi Outlander hybrid, or BMW X1 hybrid, plug-in hybrid, or this 2 Series sports or active van, how they call it, where there's the rear axle is electric, the front axle is driven by a combustion engine. Car manufacturers like this because they can build on an existing platform. They offer one model as plug-in hybrid, and they just have to insert the electric axle. It's a little bit more complex because they find place for the battery and so on, but they don't need to modify the platform. Yeah. Thank you.
Yeah. And just one more regarding the hybrids or plug-in. I think the European Commission, they don't like it so much that they want to really change some, I would say, the point of view on it.
Yeah, the plug-in hybrid was pushed by the car industry a lot because there was the great opportunity to reduce the fleet CO2 emissions with the specific cycle. And they do not have to change a lot. They could use their combustion engine-based architectures, put in a relatively large battery. And from the basic idea, it's not bad. So a friend of mine, he's professor in my university, he has a plug-in hybrid, and he drives every day about 10 kilometers to work and then back home. And 20 kilometers a day is not a problem to drive electric. So all over the week, he never starts the combustion engine. And in the weekend, when they visit the grandmother with the family, then a longer distance he drives his combustion engine. So in general, it's not a bad idea, but we learned that most of the users do not plug in. Perhaps when the gas prices increase further, this will change, but it's from the market prognosis, I think that plug-in hybrids will not have more than 10% of the total share in Europe, because it will remain some niche product for people that want to have a combustion engine in the car and drive electric. I think, yeah. Thank you.
Maybe I have questions. Very often discussed question is safety or how to say self-burning of the cars.
Yeah.
I have read some message or some how to say information from insurance company that there was a comparison between the battery electric vehicles, plug-in hybrids and internal combustion engines. Do you have any information about the safety or self-burning, especially self-burning of the cars in this type of technology?
Yeah, very good, very important question, thank you. In general, these lithium-ion batteries that we have in cars, they burn very well. This is the problem. This is due to the chemical elements, the electrolyte, the cathode material mainly. With the cathode material, for example, we have lithium metal oxides. So we have a material in the cathode of the battery which contains oxygen. And this is the reason why it does not help when you have a lithium battery burning. It does not help to try to stop the fire with water or with foam or something like that, because the oxygen is inside. It does not help to block the atmosphere against the cell. This is very critical behavior. And the performant or high-performant lithium-ion cells contain nickel, cobalt, manganese, and aluminum alloys. And this manganese cobalt alloy is also very reactive. Therefore, in general, the lithium-ion cells are dangerous in terms of fire. How does the car manufacturer or the automotive industry react? At first, they protect the battery. So when we look at the modern battery, we have very stiff protection beams and against crash, for example. And the second is the thermal management system. They actively cool the cells because the fire in the cell starts at a certain trigger temperature. This trigger temperature is dependent on the materials. So, for example, this NMC, I think they have a trigger temperature of about 150, 170 degrees in the cell. When this temperature is reached, then this so-called thermal runaway starts, the self-heating process where we have the fire at the end. Other materials like iron phosphate batteries have a higher trigger temperature, I think 220, 230 degrees, so they are more safe. And at the end, when you have an accident with an electric car, the cooling system or the thermal management system tries to keep the temperature below this critical limit. We had an accident 2 years ago in Austria with a Tesla Model S, so your car, where the car started to burn. And after the fire was erased, it turned out that the battery did not burn. So there was an electronic short circuit in the 12-volt system, and the car started to burn, but the battery did withstand the fire of the rest of the car. So in a modern electric car, they did really good engineering because the battery did not start to burn, even if there was this lithium-ion battery in the base of the car. So, of course, it's not 100%, but when we look at statistics, electric cars do not have more burning accidents, so car burning, than normal cars.
Because in the message from insurance companies, they announced that the most dangerous are plug-in hybrids because they are the most complicated, and there is a lot of faults or errors which can cause the fire, and then the internal combustion engines. As I know some messages from Brno, they announced that maybe 200 fires of the combustion engines park it. Not during the way, but the park it. But I'm not sure if this number is true. If you have some.
So no, I have no statistics about plug-in hybrids, and also. But internal combustion engine, yes. As we have temperature issues in internal combustion engines, especially with gasoline fuel, it's very reactive. And there are different issues where they can start to burn, starting with a fuel pump error where there's a spark in the or overheating fuel pump, or some leakage of vapor so gasoline, vapor. So there are many reasons, but I'm not sure about how this affects hybrids and plug-in hybrids. Yeah. But with electric car, it is an issue. But in general, more critical, and this is for all the audience, don't play with lithium-ion cells. Be careful with that. Some weeks ago, a house burned down near my city because a guy wanted to repair his electric bike, and the cells started to burn. So be careful with them. Let it in the car, and don't repair them in the car or whatever. But I think I don't have to tell here in this audience. Yeah. But it is a critical thing. Please.
As we are talking about gasoline vapors, usually when someone calculates these emissions, they account for power, electricity, transmission losses, and so on and so on. But do you have any idea how much losses are because of transportation of the fuel and these gasoline vapors and so on?
Yeah, there are really less or low statistics available for that. In the car, it's theoretically solved because the car tank system must be gas tight. So there is a carbon trap in the gas tank where the evaporation is sampled. And when you drive the car with combustion engine, then these gases are purged. So this trap is purged and cleaned, and the gases are burned in the combustion engine. So it's more or less a closed system. And also when you tank the car, the modern tank nozzles, I think it's a law, they must have some kind of suction process that the evaporation is small. So in the car, theoretically it's solved, but I do not know how it is with the production of fuel, the transport in the trucks, the filling into the gas stations and so on. So I have no numbers here.
Also like accidents?
Yeah, in case of accidents or leakage of fuel, and so I'm sorry, I have no numbers, but of course this is relevant. I'm just not so sure how relevant it is for the climate. It's bad for the environment, but this hydrocarbon evaporation just have a small content of methane. These are more heavy gases, and they are not so relevant for climate warming. Very relevant for climate warming is natural gas, is methane. So methane has about 30 times higher CO2 climate warming effect as CO2. So 1 kilogram methane has about the same climate warming effect as 30 kilograms CO2. This is a light gas with a high impact. But in these fuels, it's only a small fraction of this gas. Yeah, thank you for your question. Some other questions, remarks? Yeah, please.
You also spoke about suppliers of car manufacturers, about all these systems which will be not necessary in the future. What they will do, because we working with the automotive industry since 2007. Yeah. We still try to attract that battery vehicles are future and so on. And in Czech Republic especially, they said, oh, that's not true, and you are dreamers and so on. But right now, they saw that all systems are shifting into battery, and they say, oh, we have more work right now.
Yeah, absolutely right. Yeah, that's a very good question. This time I'm working on a study for the local government, so Styrian government in the south of Austria, with exactly this question. I'm just writing on this study this time. I just can tell you what happened in the past years. 2 years ago, it was a short time before Corona, I was invited by a German company that produces connecting rods for combustion engine. So connecting rods are the connection between the crankshaft and the piston. So these are forged parts, very important in combustion engine. And this company is one of the largest companies worldwide producing these parts. They have made large investments for these production machines. And they asked me, Professor Hirz, to be serious, is this a real thing with this electric stuff? Or can we produce our connecting rods and sell them continuously further in the future? And I said, yeah, you should take it honestly. You should take it seriously. And they said yes, they are afraid of that. And we discussed potential alternatives. So what can they do with their forging technology and metal forming technology in the future when the number of sales of combustion engine goes back? And we had a very extensive discussion in the board of management, in the upper board of management, and then more detailed in the facilities to think about alternative parts they can produce for electric cars, for other applications with their technology, so to transfer their technology in other products. And at the end, I'm in contact with them, and they feel the reduction of demand on connecting roads very much because the smaller engines are built. And when you build a 3-cylinder engine instead of a 6-cylinder engine, you just need the half number of connecting rods. So they feel it now. And they are in this transformation process. And this is one approach that I see that the companies that have much knowledge, and we have very good companies here in Europe, they have to think about how can they transform their know-how to new products or enhance their know-how to new products to be competitive also after or in course of this transformation process that we have today. This is the only way we can go because at the end in 2035 the demand on pistons, crankshafts, connecting rods, gear wheels for gearboxes, clutches will be much lower than today. And the companies have to change. They have to go in this transformation process. The one large challenge that I see is that we have different countries and different strategies. Those countries, on those politics perhaps, that support that open the eyes of the responsible persons in the companies and that offer programs to support this change will be first in the transition. And this will be the winner, because every change in a system has always winner and loser. And those areas or those companies who do not react early enough, who wait or which wait too long, they might be the loser in this process, because when they start to change, the competitors have 2, 3, 5 years experience in the new technologies, and to close this gap will be very difficult. So I'm sorry, I cannot give more accurate answer, but this is the situation that we have from our point of view.
And just if I can have just one question regarding, now as you mentioned, who is in the beginning, this is the winner. So now if we are looking on the Chinese car makers who are already, I would say, in front of us, and they are right now coming to Europe, how do you see this? Or if you can comment this a bit.
Yeah, I'm in China since 20 years, frequently. So I worked there as a professor in the university. We had many projects with Chinese companies. And with the Chinese situation, we have to consider that the Chinese economy system works different than ours. The Chinese economy system is planned by the government. And the government did set the plan that it supports the development and production of electric cars in China. In that way, or that's the reason why we have really strong companies in China. We talked about CATL. It's the largest automotive battery manufacturer. We have BYD, it's another one, and many facilities for production there. So this is because of money from the state, from the government, to start up this. And here we talk about billions, so it's not small money. And the same is with the car manufacturers. So one example is NIO. Perhaps you have heard about NIO. It's a Chinese car manufacturer that I have in my eyes since about 6 years, 7 years. It's a startup company. And they produce pretty good cars, electric cars. And they got much funding from the Chinese government to come to that status. And now they come to Europe. So last year they came to Norway, and this year to Germany, and they want to sell cars in Europe. I'm not sure about if they will be successful in Europe, but they are here. And perhaps more critical will be manufacture with lower cost of cars. So electric cars for 20,000 euro with the quality of a Volkswagen ID.3 will be a competitor. And on the Chinese market, there are these cars, perhaps not as good quality as a Volkswagen, but they work on that. And they are not stupid. They hire European engineers. So European engineers develop their cars, and this could be a point of serious competition here. Yeah, I see that. This time, I see it not very fast because the Chinese market is demanding a lot. So the Chinese market is the largest market worldwide this time. They sold, I think, 25 million cars a year, so the last years about, which is larger than all Europe and larger than the United States. And this, of course, is important for European car manufacturer, but also for Chinese car manufacturer. But at the end, they will grow and they will export to other countries, and then there will be, I see that there will be strong competitors, yeah. Because the battery is the most expensive part still comes from China. Yeah, that's true, yeah. Mm-hmm. It will be serious competition, yeah. And they are smart. So, for example, Volvo is owned by a Chinese company. So they buy or take share at European companies. They go into joint ventures. And MG, yeah, disappeared. It's a Chinese company. Yeah, we will see. Yeah. Thank you for the question. Okay. No more question?
Well, as we were talking about Chinese cars,
yeah.
What do you think about Chinese manufacturers pursuing LFP batteries in the EVs?
Yeah, the LFP batteries are in Teslas today. Yeah, lithium iron phosphate. Yeah, but the Tesla that are sold here. So the China.
Because they are Chinese.
Yeah, they are produced in Shanghai and exported to Austria. And I did read just the publication that about 50% of all Teslas sold this year are equipped with LFP batteries. So they are here. And here we have a problem that other car manufacturers did not react on this LFP early enough. Now they announce every Volkswagen, Mercedes, BMW, all announced they will also produce LFP because it's cheaper, it's more safe, and it has a longer lifetime. It has a disadvantage of less energy density, that is, but for a middle-priced or low-priced car, yeah, it will come. So I see LFP as the strongest increase in battery technology. And here, the knowledge is in China. CATL, BYD, they will make good business with that.
Because in my knowledge, and hopefully Professor Kazda will back me up, Chinese has monopoly on LFP.
This time, yes.
Yeah, actually.
This time,
the
yes.
Chinese government decided several years ago that the LFP will be cathode material for the lithium-ion batteries in China, like #1 material. So the government pushed the companies to start produce the LFP several years ago. So there was a interesting peak in the change of the share of the materials in the market. #1 was lithium cobalt oxide from the 91 till 2014, 15. Then came peak of LFP and NMC. Then the NMC was #1 and LFP go down the share, but general production go up. But right now the share of lithium iron phosphate again increase. But I think in the future it will be not #1. It will be still 50-50 with NMC or with other materials. But I think actually I recommend that to the companies like Skoda not focus to the LFP, but focus to the materials after LFP based on the LFP.
Yeah. And here comes to the next.
Yeah.
Next is natrium iron.
I mean like lithium manganese iron phosphate.
Yeah, yeah,
So you got high energy density compared to like
yeah.
old types of NMC cathodes. However, the price of the manganese, it's like cheap. We have a lot of manganese.
Yeah, yeah.
So the energy density will be better than LFP. Cycle life will be a little bit worse, but not that bad. It will be just a little bit worse compared to LFP. And the price will be the same or lower. So it will be the material for the next generation.
For the next what about safety?
Safety the same like LFP.
The same, so safe as
LFP. Yeah.
And what do you think about natrium-ion batteries? Sodium?
Sodium-ion batteries. Actually, we work also on the sodium-ion batteries.
Yeah.
We work on the lithium-ion, sodium-ion and lithium-sulfur batteries.
Yeah.
The sodium-ion batteries are really interesting for the low range cars.
Low cost cars.
And also for energy storage systems. Like we have pretty lot of sodium. Like 2.5% of Earth crust is sodium.
Yeah.
The price will be probably lower, but not that much.
Okay.
Because we have a lot of sodium. The price of the sodium is not that high. But for the sodium-ion batteries, you still need the high purity materials. So the final price of the high purity sodium salts will be not that different compared to lithium. The big advantage is that in the case of the battery, the cells, you don't need the copper foil on the anode side, so you can use the aluminum on the both sides. So from the point of view of the price, this will be the biggest advantage from my point of view. And if the cycle life will be high, it will be great solution for an energy storage system.
Because Cattle CATL announced to come with a sodium ion battery in mass production. They announced in 2025. Very soon.
But also in Europe we have a few startups focused on the sodium-ion batteries. One is in France. It's I forgot the name of the company, and second one is in Sweden, connected to the Uppsala University.
Okay.
So mainly in France, they are like push from the point of government to do the research on the field of sodium-ion batteries, because they saw it like not the real competitor, in some fields competitor to the lithium-ion batteries. Like in the case of the high energy density, like the cars with a high range, electric, for example, planes, there is no chance for the sodium-ion battery because you are not able to reach that high energy density. But you are able to compete with the LFP or with something a little bit better than LFP. In the point of view of energy density. Maybe I have one comment to the question according to the companies which must switch from the standard production to EVs to electric vehicle, or probably will die in the future. Also in Czech Republic, the Czech Invest plan to the next year to have the presentation in the regions of Czech Republic for the companies which produce the parts for combustion engines, with the Czech battery cluster to show them what is general battery production, what are the parts of the battery production, what kind of technology are used in the different stage of the battery production, to show them the possibility to convert the tire production to the battery, for example. So also in, I know one company in Serbia, they produce the foils, the aluminum foils, and right now they invest a lot of money to the battery gigafactory in Serbia, and they because the aluminum foils can be used as aluminum foils for the current collectors, and also for like cover for the pouches. So they use the entire product in the battery production. Like a new.
Yeah, very good. Thank you very much. Yeah, we have the battery expert here in the middle of us. Thank you very much. Okay, great. Thank you very much. I think it's late, or we
should because the time is close and you have a long journey to your home. And so I'd like to thank you for everybody for a nice discussion and your attention here, and also announcement presentation of Tomáš Kazda in after 2 weeks. So I will be glad if we will meet here next week and maybe 3 times to the end of the semester. So thank you, Mario, for your presentation.
Thank you.
And for everything what you have done for us. And we will wish you the many success in your party and group of researchers, and we will be very glad to join in some connection, stay in some connection.
Yeah, for sure,
for the future.
Connection. I'm looking forward to that. Thank you very much. Thank you for having me.